Bem-vindos to one more episode of the Type Theory for All. As always, this is your host, PW. And today's episode is extra special because we are celebrating 5 years of Type Theory for All. Wow, what a journey. 5 years, it doesn't even seem like that. 58 episodes with this one. And to celebrate this, I invited Andrej Bauer. I'm not gonna lie, it feels like I've been preparing for the whole episode to be able to talk with him because I just feel he knows so much. He knows everything about type theory. He knows everything about programming languages. Andrej Bauer, he has done his PhD at CMU under the legend Dana Scott. I feel like he stands right on the edge between mathematics, logic, and computer science, and he's just incredible. You'll see that during this conversation, he will give a lot of examples in many different ways, in many different fields to make sure that we understand. He's an incredible teacher. Andrej, he's also the person who has organized the Proof Assistant Stack Exchange. He has an incredible blog that's always a great resource to learn type theory and programming languages. He has answered so many questions on Stack Exchange, on Stack Overflow. It's just a lot of stuff. Oh yeah, I cannot forget as well the summer school lectures, OPOSS lectures on effect handlers. He has a lot of material online. I'm sure you guys are gonna absolutely love this episode. We specifically talk about constructivism, about dialectica, about effect handlers, and about AI. He is currently one of the leads in this Bridge Research, Institute, let's put it that way. It's called Bridging AI Proof Assistants and Mathematical Data. It's a great episode. I hope you guys enjoy. But before we get into that episode, once again, I would like to request your support. As I mentioned in the previous episode, we have been running a little bit over expenses ever since I decided to do video. We are spending more with editing, spending more with hosting, with the platforms. We currently spend around $300 a month, and through the help of the patrons and our merch store, we can basically cover around half of that value. So unfortunately, I don't know how much longer I'll be able to cover these expenses, so I've been thinking on what are my alternatives. So the first thing that I wanted to try is to see if you guys can help me out and try to call you guys to come in and become a patron. $5, $10 a month will be a great assistance to our cause. Just simply go to typetheoryforall.com/patron, follow the prompts. It will be a great support. One of the perks of being our supporter is that you get your name to show up here. Thank you so much for all the supports. We have some incredible people that are willing to support us over these years. Thank you so much. Huge appreciation. Another little perk is that, well, not really little. I've been putting some effort into making behind the scenes episodes. And now we have this Patreon exclusive podcast called Type Theory Exists. And I talk a lot more about the personal side of the stories, my vulnerable side. I talk about the trips that I do to conferences and my conversations behind the scenes of the episodes. So another thing as well is that we have some exclusive access to some Discords, depending on the tier that you're contributing. You also get to send questions to upcoming guests because I always post it there. Anyways, just to give a little bit of background, I try to reach out to some companies, try to find out some sponsorships. I try to put as much of good effort into these episodes as I can, but doesn't seem like companies are very interested in this, like too much AI hype and all of that. So, I'm reaching out to you guys, trying to close the books here. So if you guys could assist, would be a great thing. I would really appreciate. Go to typetheoryforall.com/patreon and become one of our beloved patrons. We also accept one-off contributions. Simply go to Ko-Fi, ko-fi.com/typetheoryforall. That's it. Happy 5-year anniversary for us. Let's get into this episode. Welcome everyone to another episode of the Type Theory for All podcast. This is your host, as always, PW. And today it's my great pleasure to have with me our co-host that I'm always so pleased. I'm always so pleased when you come here, Dan. You'll make my day always shine more.
Thanks so much. I really should prepare to have to say something at the beginning, but I don't. So thanks. I'm pleased to be.
Weren't you taking like improv classes or something?
Yeah, I ran out of money.
Okay, so today's episode, I feel like I've been preparing this for the whole my whole career as a podcaster. This 5 years, just to get ready to be able to talk with this huge person in our field, Andrej Bauer. Thank you so much for being here.
Hi, I wasn't aware that I'm huge. Thanks for having me.
No, yeah, I was actually mentioning to Dan that you are a great influence to all of us that get interested in these fields in your lectures and all your excitement and your passion in this field is just comes to us. It's great. So it's very exciting to be here talking to you.
Yeah, I mean, at least for me, you're the person who got me interested in constructive math. I can't think of who else, is blogging as much as you are. Also, even just like your Stack Overflow posts.
Oh, yeah.
Such an incredible resource.
My apologies for getting into constructive math then.
Well, I'm not in constructive math. I tried to, and then mercifully, I was not allowed in.
You came to somebody made sure that you came to your senses. Yeah. Good.
Okay, so I think it's very fair for me to start this conversation asking you, how did you get into constructive math and who were your idols back then?
So I think it's from my time at CMU. I was a PhD student of Dana Scott's at Carnegie Mellon University. I was in the Pure and Applied Logic program, and at the time there were a number of people there that really influenced me. Of course, Dana being the most important one. He was my advisor. But I gradually came to sort of understand and realize what constructive math was about during my PhD, because my PhD was on computable topology and analysis, which I started doing sort of what I would say model theoretically or semantically by having like domain theoretic models of computability and so on, and then looking at spaces inside of that, and more complicated models that go under the name of realizability. And then eventually it became clear that the constructive mathematics is actually the sort of the better way or the abstract way of doing that. It turned out that whenever you do anything in the model, so let me put it this way, there's a motto that Alex Simpson attributes to me, that if anything that's worth doing inside the realizability model is done better in constructive mathematics. So I came to constructive mathematics through realizability is the short answer.
But so which department?
I was in the computer science department, but the Pure and Applied Logic program was an interdisciplinary program between computer science, math, and philosophy departments. But because I was in the computer science department, I was mingling a lot with computer scientists, in particular with the Principles of Programming group. So that's Bob Harper, Peter Lee, Frank Fanning, John Reynolds, Steve Brooks. I mean, this was a wonderful time to be at CMU, and I picked up so much from them. And then in the math department, it was Peter Andrews. And in the philosophy department, not at the beginning, but then from some point on, it was Steve Audi. So he taught us all category theory.
But then your background in undergrad before coming here was pure math.
Yeah, so yes. So in at the University of Ljubljana, I studied what was called theoretical math, there was applied math and theoretical math, and I was in theoretical math. So I got my share of partial differential equations and lots of topology and algebra, just the whole thing. Little less computer science and very little logic. But it was the logic that I was most interested in. And so that was also, but there just wasn't anybody doing logic here. So I was very lucky I wasn't really even aware of who Dana Scott was before I went there. So
That's so funny. How was it like to be at CMU together with these huge names? I mean, how was the day-to-day life there?
So first of all, there were not just all these professors, but there were also a bunch of grad students. Also, some of them my housemates, like for instance, Chris Stone we were housemates for 5 years. four of us rented a big house in Pittsburgh at the time. So maybe for any American listeners, a 4-bedroom apartment with a lawn and a garage and a huge dining room was $1,200 a month.
Oh God, so another time.
Yes, so we rented that, and so we lived together. So, and Chris was a student of Bob Harper's, and so so there were all these grad students, and then there were weekly seminars in the so the POP seminar, Principles of Programming seminar, which was great, and it just get to talk to people like John Reynolds, and you get to take courses from all of these people, from Frank Fanning, from like every single one of them had an influence on me. Taught me something important, either about logic or about programming languages or math more generally. So it was really, it was a good time to be around. Yeah.
Tell us more about the topic of your PhD thesis, which I think is called the realizability approach to computable analysis and topology. Can you tell us a little bit what was going on there?
Right. So when I arrived, Dana was very interested in symbolic computation and then like Mathematica, and doing things symbolically. But then also part of that was real numbers, what to do about real numbers. And through that, we kind of converge on, let's think about computability on the real numbers, but just the computability on the real numbers seemed a little bit boring. So then I started thinking, what does it mean to compute with points in a topological space in general? What kinds of topological spaces can we compute with? And it turned out, of course, that there were lots of people before who thought about this. And there were what people called several schools of computability, like computable mathematics. So there was the Russian constructivists from 1950s or so, where they did everything with Turing machines. And then there was what was called the Type 2 Turing machines. This is Klaus Weyrauch school, a German school, where they set things up in a different way. Then there was domain theory, Dana Scott and domain theory. That was also one way to do this. And as I started to learn about all these ways to explain what it means to compute on on more general topological spaces and metric spaces. So the kind of thing you have to have in mind is like, okay, I mean, if you compute with real numbers, then presumably you're doing some sort of intervals or approximations to a real number, and you're somehow calculating these approximations. But when it comes to a more topological space, then you should have in mind maybe a more complicated space, like some sort of a surface, or even a function space, or an infinite dimensional vector space, and more complicated abstract things. And the question always is, well, what does it even mean to compute on these things? And so as I learned about the different ways that people have approached this question, it became clear that these are all facets of realizability models, that these are just different realizability models. And so in my thesis, it was, to some extent, it was a kind of a synthesis that said, look, there's a system to this. It's not just the German school and the American school and the Russian school. These are really mathematical. These are just aspects of realizability where you start with a certain kind of computational model where you explain what you think computation is. I can give you like 2 examples or 3 to see what that means. But once you set up the model, then you can use category theoretic methods to build categories which are going to be entire little worlds of mathematics. There will be toposes, so there will be mathematical worlds, and they will have this built-in model of computability that's going to sort of govern what's going on. So one of the things that's going to happen, for instance, is in each one of them, you can define what real numbers are. And once you do, and you calculate what you get, you will see what it means to compute with real numbers. So the thesis was then at the end was, oh, okay. So first of all, there isn't one way of computing on topological spaces, contrary to the popular opinion that everything's just a Turing machine. These are different models depending on what you think computation is. And then, but there's an umbrella framework called realizability that allows you to systematize them and compare them and have transformations between them and so on. And then the second part of that was, okay, so there are now a gazillion different ways of computing. Is there a common theme to them? And the answer is yes, constructive mathematics. So anything you do constructively, you can then translate to any kind of model of computation that you have using this framework. So that's more or less my thesis.
Something that I've, always wondered, kind of reading your articles over the years, is like, constructive math really appeals to my sensibilities as like a fan of functional programming. But as a mathematician, is there a philosophical, kind of intuition that you have here? Like, I mean, we're taught like there are things that are true and there are things that are false. And I think constructive math starts to get at this idea that there is something greater, but I've never really had it spelled out for me what that might mean. Or maybe there isn't such a philosophy.
I think we can broadly follow here what is known about, like, what are the most important examples of models of constructive mathematics, of mathematical worlds, so toposes that are that are not classical, right? And they broadly, you can divide them into two parts: the ones that come from geometry, Grothendieck, algebraic geometry, stuff like that, and the ones that come from computability, so based on some notion of computation. So as a functional programmer, you would be more familiar with the functional programming kind of thinking about constructive mathematics, where you would say things like, well, to prove that for every natural number, there is a prime number that's larger than the given number, okay? It makes sense to write a program which takes a number and outputs a prime larger than it, right? And that's intuitively how you would constructively explain why there are arbitrarily large prime numbers. You wouldn't say suppose not, right? You wouldn't start with assume there aren't arbitrarily large prime numbers and then derive a contradiction, because, okay, but that doesn't give you any way of actually getting at the prime numbers. So if you keep this idea, if you follow this idea that whenever I claim that something exists, I need to have my little Haskell program that is going to witness the fact that it exists or calculate it or something, then you go into this computational explanation of constructive mathematics that is going to appeal to programmers, more or less, people who are sort of computationally minded in general, who would say, oh, I don't want to just know that numbers can be factored. I want to know how they're factored. I want to be able to factor them. So that's one important source of constructive mathematics, where you insist that you need to get your hands on things. And it's also how, if you look at how maybe originally constructivists spoke and talked about constructive mathematics, they were kind of coming from this angle that you need to make things concrete, and you need to be able to actually manipulate them. And that's where the word construction comes from. You want to construct things. You don't want to just know that they exist. But the other one is also important, the geometric one. And I think that one might appeal more to somebody who is a very traditional mathematician, and the only use they have for computer is to write LaTeX code and answer emails, right? So if you're that kind of mathematician, then you're gonna say like, yeah, okay, I mean Haskell programmers, whatever, right? So then you have to get them in you have to get in through some other angle. And so a good angle to go in through is to say, Alexander Grothendieck, right? They'll start listening because it has anything to do with Alexander Grothendieck. They must listen. Okay, so I mean, he invented shift toposes. Okay, and what happens there is slightly different. You yourself said, well, in math, things are just true or false. Okay, but we can try to make this notion of truth a little more refined. So, for instance, it rains. Something like it rains is obviously dependent on location and time, right? So it's not a mathematical statement in itself that you could interpret. You will have to start explaining, oh, but I meant it rains here and now and blah, 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 and at this point, space-time point, and so on. And you say, well, okay, we could do that, but we could also maybe start to think about the fact that if I have some so let's literally take some very geometric example. Let's take temperature on Earth, okay? And now I want to explain to you constructive mathematics using temperature on Earth. So what is temperature on Earth? Well, naively, temperature is a real number, right? It's 7 degrees outside or whatever it is, okay? But if you look at a slightly bigger picture, it's actually one number per location on Earth. So it's actually a function on a sphere. If you pretend that the Earth is a sphere. The Earth is a sphere. Every point has a temperature. So it's a scalar field on Earth. So it's some sort of a function. Now it's also reasonable to assume that this function doesn't have sudden jumps. So it's continuous. It's a nice function which tells you for each location on Earth what is the temperature there. So if you now say the temperature is greater than 7 degrees, okay, you get a region on Earth where the temperature is greater than 7 degrees. And if I say the temperature is exactly equal to 0, then you'll get some sort of line of like these. I mean, you've seen maps, right, where there are lines of equal altitude, and you can do the same. So the same is going to happen. So you will have regions where something happens. And so you can now say, oh, okay, so truth statements about temperature, they're not just true or false. The interesting bit is, where are they true or false? That's the interesting bit, okay? Furthermore, to make things more interesting, we want truth to have certain nice properties. It has to be, if you're a physicist, okay, so now let's put on our physicist hat, and you say, I want to establish some fact about temperature. Well, okay, but it's reasonable to say that the fact that I establish needs to be stable under small errors because I am a physicist. And so if I make small measurement errors, the fact that I establish, like for instance, I established that the temperature in Ljubljana, where I am, in some region on the parking lot outside, for the last hour has been greater than 7 degrees. Okay, well, I mean, actually, my measurements are within some confidence interval, so it better not be the case that it's equal, or I should be away from 7 degrees. I should whatever I'm saying as a physicist needs to be stable under a small permutation, because otherwise things become totally arbitrary and I have no way of making any kinds of experiments. Is that clear? Like the idea that when you want to claim a fact, it needs to be stable under small permutations. If I move just a little bit around, it still has to hold. Okay? Well, that brings in topology. That says, okay, if you move a little bit, so truth needs to be stable under small permutations, perturbations. As soon as you say that, it becomes intuitionistic. It's not classical anymore. Classical does not have that property. So this is the other geometric road to constructive mathematics, is to say we are not going to assume excluded middle because it is not stable under small permutations. Perturbations.
I can understand perturbations of temperature, but what is perturbations of truth of a logical proposition like excluded middle? Which, by the way, for background, in case anybody listening to this podcast somehow doesn't know about excluded middle, it means that either A is true or not A is true.
For all A, either A or not A. It's important to say for all in front of that, because right? So what this would mean is, we can stay with temperature, okay? So if we believe in the law of excluded middle, we should believe in the statement that everywhere on Earth, the temperature is greater than 0 or less than equal to 0 degrees centigrade. And it seems obvious, right? And you can keep believing that that's true, but my point is that that's not stable. Because if you insist that it must be stable, then you could be, what happens is that the or, when I say it's greater than 0 or it's less than or equal to 0, the or itself needs to be stable. That is to say, if I see that one of the possibilities holds, then if I wiggle around a little bit, it's still going to be this possibility. Okay? It's not going to randomly jump between the two possibilities. That would be discontinuous. So the problem is on the other side, greater than or less than or equal to 0. If you're at exactly 0, arbitrarily small kick could get you to greater than 0. Right? If you're exactly at 0, it can happen that arbitrarily small perturbation will make you positive. And so this is the reason. So to conclude, the excluded middle, it doesn't fail under this geometric view. It doesn't fail because somehow magically it's false, in the sense that you can find the real number which is neither greater than 0 nor less than or equal to 0. No. This is about, it's not stable under perturbations, because if you're not careful, an arbitrarily small, if you do it wrong, an arbitrarily small kick in one direction could get you to the other, or to the other disjunct, and in some chaotic way that is not topologically nice.
So I have to press you on this, because I mean, I think it's intuitive for a physicist to care about perturbations, because we have, we're mortals with these limited instruments. But what does that mean in terms of truth? Is it because you kind of philosophically believe that there is such a thing as like measurement error in truth?
No, it's more like, if you take this idea seriously, that, okay, so far I have spoken about what we might call local truth. You're observing truth at a certain neighborhood in some space, okay? But this idea of local, that you do something locally, this is a much wider idea in mathematics. For instance, when you do analysis, you've got all those epsilons and deltas and limits, right? You're doing things locally. When you define what it means for a function to be continuous, you are talking about small intervals. You're doing things locally. And so this was actually one of the important contributions of Grothendieck's, was that he explained abstractly what it means to do something locally. Huh? So people walk around with these T-shirts, think globally, act locally, right? That's actually like, to me, that's okay, you want to do sheaf theory. So,
it's a good idea for a merch that we can release now.
There you go. Yes. What I would like to say is that it's not just truth that we observe, whether it's stable locally and under small perturbations, but any kind of mathematical construction can be so observed. For instance, we can solve differential equations locally on small neighborhoods and then maybe glue them all together. This is literally act locally, but think what you're going to get globally. It's literally that. You solve a differential equation by making small local solutions and then you glue them together. So solving a differential equation will have the same character of, yes, we work in a small neighborhood, and we want everything in this neighborhood to be stable under small perturbations. So all of mathematics becomes like that. So you shouldn't really just worry about whether truth is like that. What happens is you get little different kinds of mathematics at each point in your space. This is sheaf theory. So that's why. So what you see, I want to give you the answer. The answer I want to give you, this is not the truth you're looking for. Just like, these are not the druids you're looking for. Okay. Because it's kind of irrelevant that you worry about the truth when you should be worrying about everything else as well. The entire, like all constructions that you can ever do. I can appeal to your functional programming side. Okay. So when you're writing a program inside some code, you have available some variables, whatever they were declared. You have lambda x, lambda y, let z equal la 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 la. You have x, y, and z. Okay. So the more variables you have, the more special is the situation you're in, correct? Because, you say, I have an x and it's an integer, and I have a list, which is the list of booleans. I also have a function f, which does something. Having all this stuff makes your situation more specific, because it's specific to the fact that you have x and y and z and f, right? Versus on the top level, you don't have that much stuff. You have less stuff, okay? What am I describing? I'm describing a notion of locality. The more you have, the more variables you have, more local you are. So even in programming languages, this applies. The more variables you have in your context, the more local you are. So now when you ask me, well, what about truth? Well, this is another, you already believe in local truth. You just never thought about it this way. You are able to think under assumptions. You are able to think under the assumption that you have an x and a y and an f, and maybe that that x is a prime number. And this is, so you already know what hypothetical truth is, which is hypothetical truth means that something's true given some assumptions. But you can view these assumptions as placing you into a very local situation, just like in the geometric picture, you can be placed into a small neighborhood on Earth, and you observe what happens there, and you say, oh my God, we're inside Sahara and it never rains. That's a special situation. Just like, we have these variables here in Haskell. I can compose certain things and create a nice gadget, which otherwise I wouldn't be able to because I didn't have these variables before. So you already know this. So it's just a different kind of conditional truth. It's truth locally in a neighborhood versus truth in a context of assumptions. These are all the same facets of the same thing.
What I want to bait you into doing is saying something philosophical about yourself, maybe, or as a person, or about your philosophy on the greater world. And I'll give you an example. I think my research is in distributed systems, and I like to say what drew me to that area is that I have anxiety. And I like to think about every single possibility and make sure that none of those scenarios will play out not in my favor. So I wonder if maybe for you, are you just secretly a hardcore moral relativist or something like that?
That's a very good question. Okay, so it's also a very personal question, by the way, but I'm going to answer it because I thought about this. Okay, so this is my naive personal explanation of how I got to be here. Okay, I grew up in an extremely schizophrenic society. I was growing up in the 1980s socialist Yugoslavia, okay, in a religious family. So there were, from the young age, two ideologies that were competing for my brain. One was the one that happened in school, and the other one was the one that happened in church. Okay. The net result of that is that none stuck. Okay. So, but also, so they beat each other by, like, they destroyed each other. They canceled out. So, but also, I think that deep childhood experience and as a youngster, I think from that, what I took away was, in fact, some sort of, you can call it relativism, where I absolutely did not have any preconcept, like I was cured of the idea that there is a holy truth or one truth, right? I wasn't in mathematics. Of course, my mathematical training as an undergraduate was completely traditional. And because it is completely traditional, your professors of mathematics are going to behave like mathematical truth is the best truth out there. They're going to stop short of saying that it's better than religion, right? Even though they probably think that. And they will, or sometimes they will say, well, it has an objective notion of truth and proof, and it's a lot more objective. You don't have to have faith in it. Nevertheless, once I got exposed to the fact that there is intuitionistic mathematics, okay? So because I was a grad student at CMU, there was Frank Fanning. Frank Fanning he's like constructivist to the bone, okay? So I was in his classes, and eventually it started rubbing off of me the fact I realized, well, okay, there are people who can be like that, okay? So it must make sense to them, right? And Frank Fanning is obviously a very smart person. He's not just doing rubbish, and not to mention that he's doing these great things with computers. So once I saw the same picture again, oh, it's two kinds of mathematics competing for each other, but one of them claims to have won, the one that Hilbert, right? I was told by my professors that classical mathematics won, and that nobody in their right mind would do constructive mathematics, and there are just like some enthusiasts somewhere in the Netherlands, like 5, and then nobody else does any constructive mathematics. That was what I heard, right? But then at CMU, I see there are constructive mathematicians, and they are of the best kind, doing amazing things with programming languages and coming up with new compilers and new really, really nice ways of programming and all that. So it clicked again. Oh, okay, there are many worlds, okay? And then it combined itself with the fact that I discovered that there are many schools of computability, and each one is just a world. So somehow out of that grew my outlook, which is, well, there isn't one mathematics. There are many kinds of mathematics. In fact, there are probably sort of fringe mathematics that we as humans don't really know how to work with. Linear logic, start doing strange stuff. You don't know what mathematics would look like or whether it's even possible. But there is sort of a nice core of mathematics. You could say topos theory or models of type theory, but worlds of mathematics in which a human mathematician can express themselves using the language we know. So for all, or, and, functions, pairs, lists, these basic concepts we already know, they make sense in all of these worlds of mathematics. So no, it cannot be the case that one of them is the best, right? Based on my personal experience and how I grew up, right? So yes, I am proud to be a relativist, yes. In fact, there is a blog post about that, because people kept assuming that I'm a constructivist. So I wrote a blog post a while ago, Am I a Constructivist? In which I say, no, I'm a relativist.
Fantastic. I'm speechless for how amazing that answer was, although unfortunately it was already a blog post. So
no, the blog post has a lot less. The blog post only has the conclusion of that answer, which says, I'm a relativist. Okay, I don't explain how I got there. I just say, this is where I am. But mind you, I don't expect that all mathematicians will spend their careers studying all these many worlds of mathematics. That's really not for everybody to do, right? But I think it would be nice if the attitude at least changes from, oh, Hilbert won, to, oh, there are many, many interesting things out there. I wish I had more lifetimes to study them all. Okay. But you have to make a personal choice. And I understand you're drawn to some particular thing like combinatorics or differential geometry. And of course, you're going to do that. You know, not everybody's going to do foundations of mathematics. Thank God. Right. I'm going to throw one more. Luckily, good mathematics does not depend on foundations of mathematics. This is important to keep in mind.
Yeah, how could that possibly be?
Because we have evidence. Core mathematics existed before modern foundations of mathematics. So it got retrofitted into set theory, like 18th, 17th, 18th, 19th century mathematicians. There was no set theory, yet they did amazing mathematics, Riemann surfaces, complex analysis, whatnot, algebra. They did all of that. There was no set theory. Then set theory came along and said, oh, yeah, all these things you did, it can be done in set theory. Okay. What's happening at the moment? Oh, all these things you did, they can be done in lean type theory. So it's just getting retrofitted into some foundational math. Like you have a foundational system and you're observing, oh, this foundational system is rich enough to be able to take all this beautiful math and express it.
It's so weird, though. It's like building a house from the top down, right?
Is it? I think it's more like, no, I think it's more like this. They built beautiful cathedrals in Middle Ages, but they didn't know any physics. Then physics came along, and it explained why those cathedrals are still there and they didn't crumble. So it's more like that.
Okay.
Yeah.
Yeah.
That would be my way of explaining, because the laws of statics, right, the physics, came later, and they give an additional understanding of the cathedrals. But the cathedrals were already there, and they were already beautiful, right?
Let's press this analogy, though, because in math, when we write a proof, we start from basic assumptions and rules, and then we derive conclusions. But foundations is all about kind of verifying, that the rules and the axioms are good, that they make some kind of sense. So how was it what were we doing?
I'll make a quick interjection, because I think there is a clear difference in how computer scientists and mathematicians think. And I feel that mathematicians are a lot better working with their intuition. So they're not necessarily thinking about all the axioms or the things that should hold. They're thinking of like things that make sense, like that they're not really, they don't really, it doesn't seem to me that they care so much about the foundations, that things make that much sense. They're trying to solve the problem and that things fit together well, and they have good intuitions, and there's a notion of just some beauty going on in their brains somehow. Anyways.
Oh, I thought Dan was trying to say something. Then you interrupted him, and now he's gonna say whatever he wanted to say.
I think, along with the lines of what Pedro was talking about, so I revealed that I have a very kind of computer science way of thinking about proofs, and that there's this other way of doing it. And I think maybe the real question is like, is mathematics discovered or invented in this sense? Because it seems like, it's almost like a science, right? That the fact that we've been able to use it effectively and draw conclusions and build these cathedrals, but we didn't. So it was like evidentially, empirically validated in a way, but we didn't have the theory behind it. It's strange, especially because of how proofs, at least in my mind, are very bottom up. It very much feels like we built a house from the top down.
Okay, so I think there's several points here. I hope I can remember all of them. Okay, so I can continue giving you analogies. Okay, so to wonder, how come a mathematician can write a proof, but they don't really know much about foundations, which, by the way, it seems to be the norm. If I go up and down the corridor where my colleagues are, they're all brilliant mathematicians, and I say, put the gun to their head and say, the axioms of set theory plus first order logic inference rules now. No, they will not know them, okay? They don't have to know them. Why is that? Well, okay. Did Shakespeare write beautiful things? Yeah, most people think so. But did Shakespeare know all the grammatical rules of the English language explicitly? And was he a linguist? No. So I think a mathematician is like a poet, but a logician is like a linguist, right? So that's the difference. So yes, mathematicians speak mathematics natively and are really good at it. It's the linguists who try to explain what it is that the mathematicians speak and write. So it's a bit like taking a famous writer or poet, and then you start analyzing the songs, right? That's different from writing the songs, and it's similar. So mathematicians do in fact have very good intuition on what constitutes a valid proof. A lot of it is trained. So I claim that if I could get them young, okay, you give them to me when they're still in high school, and then I get to teach them analysis, calculus 1, and algebra and linear algebra, I think I could probably get away with making an entire generation of mathematicians who are constructivists, and they wouldn't even know, okay? And so a lot of it is upbringing, because, well, I mean, that's always the case, right? So if you have somebody who is a virtuoso on the violin, well, they went through some serious schooling, and they couldn't be a virtuoso on the violin without having really good teachers who taught them how to play the violin. It's the same with mathematicians. I mean, they are brilliant, but they didn't grow up in vacuum. They were produced. They're a product of the education they went through. But anyhow, they end up with this beautiful, strong intuition that allows them to make leaps in reasoning that are correct. So they see the light at the end of the tunnel, and later they come back and fill in the details. And it turns over and over again that when you look at these proofs and you try to formalize them, well, apart from some minor mistakes that you can get rid of, yep, they tend to be correct, right? So yeah, good. So I mean, that's like saying, oh, Shakespeare didn't make too many grammatical errors. You know, it's like that.
So there must be like some kind of, I don't know, thing called math, in the sense that, like, okay, when somebody writes a song and it's really good, and they don't have to know anything about music theory. In fact, you know, most music theory is descriptive, not prescriptive, like you mentioned. It works because we hear it and we like it. With math, when we talk about it, mathematicians seem to pretend that there is a formal system. It's like it's not arguing to your intuition. It's not arguing, do you like this proof? It's arguing, do you think that this is true? So there's some kind, is there like an organ or something like that, in the same way that I can appreciate music that gives me access to truth? Or I don't know.
I don't think mathematicians are oracles who magically feel what's true and what's not true. Any serious mathematician has had a situation where they thought that they proved something, they thought it was true, and then, you know, one morning in the shower they said, oh my God, there is a problem, and then it all crumbled. So I think if you're a serious mathematician, you know that your intuition about what is true is a very valuable thing because it directs you, but it has to be, your results must be verified by proof. Must be, because the intuition will go wrong. So I don't think there is a mathematician who has never gone wrong thinking that something's true, but then after maybe a while, it became clear to them that it's not actually, that they were wrong. So I wouldn't say that mathematicians have this built-in notion of truth. By the way, we should not conflate just like this idea of mathematical truths with what do mathematicians find beautiful or worth doing. That's a different matter. As a functional programmer, you can know that it's going to be very easy to write a program that spews out thousands of theorems per second, right? Why doesn't that make you a mathematical genius? I mean, you have proved more theorems than anybody, right? So there has to be a reason, and the reason is, well, it's the wrong theorems that you're spewing out. They're worthless. Why are they worthless? They're not interesting. They're not beautiful. But I'm now using words that are not mathematical, right? Beauty, relevance, applicability, things like that. That's extra mathematical. Sorry, you were going to ask something?
Yes. No, I'm going to change the question now for something else that I had in mind. But you make this distinction between the people working in the foundations and the mathematicians, like just as the poets and the linguists here. How do you see yourself? Because it seems to me that you kind of work in the middle here, both in the mathematics and the foundations and working in the beauty. And it seems to me this is why you're so good at bringing all these examples to us, like you're in the middle.
So I think what's interesting to me is when you use the methods of foundations of mathematics to try to do actual interesting math. So of course, maybe the example I'm most proud of is building a topos. So that's very much the job that is for somebody who is in foundations of mathematics to find a certain kind of model of mathematics such that something very interesting happens in there. For instance, something that mathematicians find mathematically relevant, such as the real numbers are countable. Now, mathematicians will find that extremely surprising because of their classical upbringing, of course, and that was kind of the point of it all, is the shock value was intended. But it's a statement that it's just a traditional mathematical statement, right? I mean, most people would think it's insane that it can be true, but they will not argue with the fact that the real numbers are countable is an entirely mathematical statement. It has nothing, I mean, it's kind of close, maybe a little bit close to foundations, right? So another kind of thing that attracts me is, for instance, is synthetic differential geometry. So what is that? Well, that's setting up a world of mathematics. So that's something that foundationalists do, not ordinary mathematicians, in which every function is differentiable. So only smooth functions on the reals exist there. You can just take derivatives to your heart's content all the time. You can take the derivative of anything you like. Okay. I find that appealing. Why? Because it's not just foundations for the sake of foundations. It's foundations for the sake of illuminating some important aspect of mathematics. So what is the important aspect of mathematics in the case of synthetic differential geometry? It's this. We teach students of physics that differentiable functions are such that epsilon, delta, limit, blah, blah, blah. There is a definition by Weierstrass or Cauchy, or around the time of Weierstrass and Cauchy, of what it means to have a differentiable function. And then we keep telling the physics students, oh, you have to be very careful. Not all functions are differentiable. You cannot just take derivatives all the time. That's a bad idea. What happens when they go to a physics class? Well, the professor says, well, I will just take derivatives all the time. Okay? So I think it's a really bad attitude for a mathematician to say that the physicist is doing something wrong in that case. It's really a bad attitude, because these physicists have been doing all these forbidden things with differentials for centuries, okay? And thanks to them and their cousins engineers, we have all kinds of technology, and it seems rather amazing that they keep doing forbidden things that really explain very well how the nature works. So I would rather say, as a mathematician, that this is my problem, not their problem. I need to explain why they get to do that. Well, let me build a world in where I can explain to myself why that's okay. A similar one that will be closer to Dan's heart is computation, right? So Haskell programmers, they just pretend that all functions are computable. They never worry about, oh no, now I'm trying to define a function, but it's not computable. I mean, they know about the halting oracle and all that. They heard about all that kind of stuff in school, but they ignore it, more or less. For the most part, you don't have to concern yourself with these kinds of things. It's a different kind of world. You are in your Haskell world, you're doing functional programming. You are not really hampered by the fact that there exists some crazy things, right? That it's irrelevant. Just like it's irrelevant for the physicists that there are these functions that you're not supposed to differentiate. So it's the same thing. Well, what's your world? What is the world of a functional programmer? Well, my answer to that would be it's the realizability model on top of Haskell, right? That's going to be the one that's ready-made for a Haskell programmer. It will contain exactly those truths that are true in the Haskell world. And so, yeah, so that's the kind of math, that's the kind of foundation I like to do. A foundation that has some relevance to somebody outside of foundations. I find that to be most satisfying.
This might be an unanswerable question, but I wonder if there's like a vibe to the classical world. Like in constructive, computable worlds, you always have your hands on something. But is there a part of you that there's not a part of you that worries that like classical math proofs are wrong, but it's like that things pop out of nowhere or something like that. Is there any, because you've been so receptive and so good at coming up with real world analogies to all this stuff, I wonder if you have a real world analogy to classical math, the feeling that it might give you, and that why it's interesting that so many mathematicians assume it, but is something like excluded middle by default. What is their sense of beauty or their sense of intuition that allows them to operate in that space that others don't?
I'm going to use an analogy that was that I learned from Paul Taylor. He has called set theorists sand theorists because they are on a beach where there is just lots of sand. It's all amorphous, and then they build their castles. But the next morning, the castle is not there anymore. It has crumbled back into the set. So what I'm saying is that because everything, like so much is possible classically, you can do things that you can't really do, right? Using excluded middle. You can decide you can pretend that questions are decidable when they're not, right? But we have to be careful about using the word decidable. It's maybe there's a definite vibe to classical mathematics. I mean, I myself just have to try to think about what it was like when I was an undergrad. That was the classical vibe, right? So there is it is a consistent sort of world outlook, mathematical outlook. If you are deeply into classical math, you will of course have your own feeling for what happens. You will develop your classical intuitions and so on. So you want an analogy. So maybe the analogy is that this is a bit of a mischievous analogy. I mean, Paul is like that, right? He would have made this analogy. He knew exactly what he was saying, is that the classical mathematicians are making castles with this in the sand, right? Out of sand. So that it's more like the subject matter is more amorphous. There is just sand. You can make whatever you want. Okay. Well, let's contrast that with constructive mathematics. I have previously described constructive mathematics to people who were trying to understand it by saying it's like Lego blocks. You can't put Lego blocks together in any new which way. You have to follow the rules. They have to fit. They have to click. You want to build a house, you need particular kinds of Lego blocks to make a house. But if you want to make a sand castle, all sand is equally good, right? There is no preconceived structure there. It's just raw material, and use your imagination, right? So it's maybe a little bit more like that.
there is no proof that that classical logic is more expressive than constructive logic, is there? In general.
So there are general theorems that say that if one is consistent, and then so is the other. So that is not an issue. Okay. Under certain technical conditions. Okay. Then what we do know is that so if you take classical set theory, you can sort of go very much high up with large cardinals. Okay. A lot higher. People know how to do that better than in type theory. So in a sense, you could say that at least in terms of how big things can get, classical mathematics could get further. And that's one of the questions that I'm interested in is classical set theory knows how to say, oh, we have really, really huge objects out there. And type theorists don't really know, like constructive mathematicians don't really know well how to take ideas of those really huge objects and translate them to their setting. So you could say that in this sense, classical mathematics is more expressive than constructive mathematics because in practice, it allows you to speak about things that are not so easily spoken about constructively. Okay. But there's a flip side to this. Okay. So the flip side to this is that constructive mathematics is obviously more expressive than classical mathematics, but in a different way. It allows you to consider more possibilities. So constructive mathematics, so in classical mathematics, you cannot consider the possibility that all functions from natural numbers to natural numbers are computable because you can construct one that isn't. Okay, so you define the halting oracle. It's not a computable function. So the axiom that says all functions from natural numbers to natural numbers are computable is clearly false. So what does this mean? Because classical mathematics proves more things, right? You are not allowed to assume things contrary to classical mathematics. But constructive mathematics is a lot more permissible because it doesn't prove many things. You can add axioms to it and, entertain really weird axioms like all functions are computable, or all functions for reals to reals are differentiable, or the real numbers are countable, right? These are all known to be consistent. So it allows a wider spectrum of mathematical thought because it does not prohibit certain thoughts. It does not prohibit the thought all functions are computable, whereas classical mathematics does. So there's another analogy here. So you can also say that there's an analogy between constructive and classical mathematics. Well, what's the difference? One has an extra axiom. Okay, so we can say, oh, okay, what are some other situations where we have a theory and then we have an extra axiom and that gives us a different theory? Okay, so there are, of course, examples like that. The obvious one, like take a small one, is group theory. So you go to school, you learn what a group is. Okay, and then they say, well, a special kind of group is an abelian group. Okay, a commutative group. What is that? Well, that's you take the axioms of group theory, whatever they are, and then you add another axiom that says x times y equals y times x. So what's the result of that? Well, you added another axiom, so you can now prove more things, right? But maybe this axiom also, what happened was this axiom also, fewer groups satisfy this axiom. So now you are only considering commutative groups. So you are not able to observe any phenomena that happen with non-commutative groups only, right? So it's the same. You do classical mathematics. That means you are restricted to the classical worlds of mathematics. Because you're restricted to the classical worlds of mathematics, it's a situation that is more special. So you can prove more things about it because it's a more special situation. But at the same time, you're prohibited from studying all those other possibilities, other worlds of mathematics, because they don't satisfy your additional axiom. I don't know, I'm babbling, so should probably ask another question.
I love it. I love it. I never thought it on those terms, but makes a lot of sense. In this particular point of view, constructivism is more general than classical mathematics. And this is probably a good segue for me to ask you about theorem provers, because we didn't even start talking about theorem provers at all here. But it's clear to me that this has been your interest for a very long time. And where does that come in?
Oh, well, that's another story if you want to hear the personal
course.
reason for that.
For sure.
Okay, I think I was probably in high school. For some reason, I saw there was some journal. I have no idea what the journal was, but it had like a 1-page blurb about Wolfram's Mathematica, or maybe it was still called Maxima at the time, or whatever it was. And it said, oh, you can tell it to integrate this function, and it calculates this integral. And then you can tell it to factor this polynomial, and it'll factor it. And then you can calculate the limit. And I thought, oh my God, this is a program that can do mathematics. And this left a very deep impression on me at the time. And I was very interested in how you can have a program that will do mathematics for you. It was it calculated limits, it calculated integrals, it did all sorts of things that were not just calculate with numbers, and it was not just draw the graph of a function. It was doing like what I considered to be, as a high schooler, serious math, right? Calculating integrals. So I was always very interested in that. So I did a lot of, I actually, my first research paper is in symbolic computation. It comes from that interest on how to do some algorithm for calculating summations in symbolic form. And I think the road from there, for me, the road from there to proof assistance is more or less a straight line, because these are programs like Mathematica, Maple, Maxima, Sage. These are called computer algebra systems. They can do lots of symbolic manipulation of objects, but they don't prove any theorems. So, and you don't know that they're really true. But if you're a serious mathematician, you should be worried about that. I'm using a piece of software, and it's telling me that it calculated an integral, and I have no idea whether it's true, because it's written in C++ by some Russians who were hired by Wolfram Research and are in Indiana right now. And so, yes, they're very, very smart Russians, but still, C++ code. So what would be a better way? Well, a better way would be to actually know that you also have the proofs. Well, but that's proof. That's now proof theorems. You start to prove theorems, proof assistance, and you add to that the influence that of CMU, where at the time, for instance, so at CMU, Frank Fenning had the 12 system, which is like a logical framework for describing formalisms. And I think it was Andrzej Filinsky, I think so. He was a student also. He used that tool to prove the correspondence between the lambda calculus and Cartesian closed categories. And I thought that was like, wow, that's amazing. That's a real math theorem that you can do and prove like formally. You can really do this formally. Later, of course, then I learned, the French have the Koch theorem prover. And then, that's how I came around. But the line is, oh, okay, I really, really want to have a program for doing mathematics. In high school, I learned about the computer algebra systems. I worked on computer algebra systems. But let's be honest, theorem provers and proof assistants offer a better guarantee and also offer the possibility of expressing mathematics that isn't just algebraic manipulation. So computer algebra systems can't really do topology, for instance. There's nothing to be done there because it's all theorems. But they're good with algebra.
That's awesome. That is beautiful. And then what was your first, so you said that your first interaction with theorem provers was with 12? With,
no, I watched people use 12 at CMU. And Frank Fanning taught us how to implement small pieces of it in one of the courses, but I didn't really use it at the time. And I also didn't really know much type theory. So actually, I got my first exposure to type theory was through Bob Harper. later. It was later. It was probably like mid 2000s. At some point, I said, okay, now I really have to learn what this COP thing is because I'm interested and I want to understand how it works. And so I just started. What did I do? I think the first real thing I did was I formalized the Dialectica interpretation in COP.
What is that?
It's a very early blog post of mine about
Dialectic interpretation.
The Dialectic interpretation is something Gödel did. So this is a way of translating. Let me say it in a good way. So this is a way of translating logic, okay, back into logic, but it can also be type theory, in a way that gives you a particular understanding of what for all and exists are about in a very computational way. It explains for all and exists in terms of functional programming. Yeah, you should like that, okay? And it's not Curry-Howard. It's different. So Curry-Howard is more generally known as, right? Are you guys familiar with the Curry-Howard? Should we say what it is?
Go ahead. Why not?
Yeah, okay. So Curry-Howard is it comes in many guises. The old name or the more general idea is called the BHK interpretation, Brouwer-Haitink-Kolmogorov interpretation. It goes under that name. Realizability is one formal aspect of the BHK interpretation, but Curry-Howard is another one which is similar. And the idea is this, that you view proofs as methods, algorithms, or programs. One of those. All three words work. With the old BHK interpretation, you would say method. With realizability, you would say Turing machine. With Curry-Howard, you will say functional program. And the most important one is that you say, to prove A implies B means to write a program which transforms evidence of A to evidence of B. Right? You say programs are proofs. So that's the Curry-Howard isomorphism says, proofs from A to B are like functions of type A arrow B. And if you're a functional programmer, you will quickly pick up on this idea. So what's the Dialectica? The Dialectica says something else. It says, Curry-Howard is about transforming evidence of A to evidence of B. That's what the function does. But we could also think about having counter evidence. So what would be counter evidence? Counter evidence would mean, so to give you evidence of something is I convince you that it holds by giving you some sort of a gadget. You look at the gadget and say, I am now convinced. Counter evidence would be to have a gadget, I give it to you, and now you're convinced that the thing is false. Okay? Yes? So for example, how could I convince you that pi is less than 4? Well, how could I convince you that pi is not less than 2? Okay? I would give you some evidence that convinces you. For instance, I could give you a good enough approximation of pi so that, assuming you'd see that actually is an approximation of pi, but once you have the evidence, you can say, now I see why it is not less than 2. So for instance, if I convinced you that the digit expansion of pi is 3.14 and then something, that's enough for you to believe now that pi is not less than 2. Do you agree? Okay, so we can have evidence, that's Curry-Howard, computational evidence that something holds, but we could also have this notion that there's counter evidence. But if there's counter evidence, now we should start to think about functional programming with counter evidence. So what will be counter evidence for functions? And so I'm not going to go into all the details, but the basic observation you should have is that it's going to flow in the other way. If you have counter evidence for B, you should be able to produce counter evidence for A, right? If A implies B, if B is false, A cannot be true. So it should be possible to translate counter evidence of A, of B back to, so functions will really go like, it'll go in both directions. So the dialectica does this. It's kind of two-way. It's a two-way thing. It's like a bidirectional, bidirectional Curry-Howard, because it operates with evidence and with counter evidence.
It's also quite a lot like backpropagation and machine learning. I think that might be incidental.
There are lots of one can always observe lots of analogies everywhere, and then if you're lucky, some of those analogies can actually be made into theorems, but it can't be. It might be hard, and it might require lots of generalization. But I don't think all analogies warrant infinite amounts of attention. Okay, so anyhow, this was something that I wanted. I didn't really understand the dialectica, and so I wanted to learn Coq, and I said, surely, if I encode dialectica in Coq, I will have learned Coq, and I will better understand dialectica, and it turned out to be true.
I'm surprised we don't talk more about dialectica. I mean, sure, it's a little more specific, the use case, than Curry-Howard, but still, it's kind of like giving a more complete view of what we're doing in functional programming.
So yeah, I mean, if you want to know more about the dialectica, I can tell you who the best person to invite is. Well, there are probably two best people to invite.
I invited Pierre-Marie one time, and he talked a lot about it. Yeah, okay, it was
well,
good.
You've already had your dialectica.
But I think you made a better job doing it very, very succinctly, very, very clearly, succinctly. We with him was an entire episode just to talk about dialectica, which was also incredible, and I also recommend. But who's the other guy?
Well, I would maybe point out Ulrich Kollenbach. He's in Darmstadt. He's a mathematician, more of a logician. Classical logician, and he has very successfully used the refinements and variations of these ideas to do something rather amazing. He takes non-constructed. Before I say what he did, I have to tell you what is a special feature of the dialectica. A special feature of the dialectica is that it has the ability to turn seemingly non-constructive things to constructive things. Okay, because this counter evidence, which sounds like something that's negated, becomes a thing that you can manipulate, that you can compute with. So it has this magical property that it turns certain things which are not really computable. You go through it. There are lots of technical details. You have to study this. You have to be Pierre-Marie and then write a PhD thesis about it. But but at the end of the day, and I mean, he did it for he gave a type theoretic account, a very nice type theoretic account of the dialectica. So, but anyhow, even before that, people understood that it has these features, that it turns non-computable things and classical things into something that is now somehow more functional programming. So anyhow, Ulrich Kollenbach, who is more of a, if you want to talk to a more traditional real logician who is not tainted by all this Haskell stuff, then Ulrich is your guy, and he has been very successful in taking a serious, difficult proof in functional analysis when somebody could prove that some operator that they care about has an upper bound of something, that there's some upper bound somewhere. And the proof is completely classical. Nobody has any idea what the upper bound is. He takes the proof, drops it into dialectica, has to do a whole lot of technical work, but at the end of the day, out comes a number. And it's the upper bound. And people said, well, how is this possible? So, well, the dialectic.
No, I think this explains why every time you talk with Pierre-Marie, he'll figure out a way to speak about dialectica, because it does so much, so powerful. There's so much cool stuff going on here. I love it. It's really cool. I'll definitely keep my eye on Ulrich, you said? Is his name?
Ulrich Kollenbach.
Ulrich Kollenbach. Yeah, I'll try to remember it. I'll actually ask you for the spelling of that.
Sure.
The first thing that comes to my mind then is to start talking about effect handlers, because now it seems like your work on effect handlers come absolutely out of thin air. right? Like you're just interested in math and theorem provers, and all of a sudden, okay, well, effect handlers. But it seems like there should be it seems to me that the work you've been doing so far has some kind of connection to one thing to another. So how does effect handler come in? Or it doesn't, maybe.
Okay, so first of well, the effect handlers, my work on effect handlers is joint work with Mattia Pretner, who actually with Gordon Plotkin, invented the effect handlers. So I came in when the question, so the way this works, so first of all, at CMU, at CMU, I learned functional programming. I didn't know functional programming before. I learned standard ML and then later OCaml, and generally got some sort of reasonable education in programming languages because I was, I was educated. I was in classes by John Reynolds and people who did made these amazing things with programming languages. And my housemate was Chris Stone, and his advisor was Bob Harper and ML and all that. So I was in the perfect place to learn about programming languages, and this very much interested me. Even though it wasn't my PhD thesis, I was kind of absorbing a lot of this. Then I did some domain theory, being a student of Dana Scott. That's not surprising because, okay. But domain theory was the denotational semantics for programming languages. So if you wanted to have recursive types, you needed domains. If you wanted to model general recursion, you needed domains. So that's another point of contact with programming languages. So I have always been very interested in programming languages. And then Mattia, who was first a student of mine, then went to Edinburgh, where he was a student of Gordon Plotkin to get his PhD. He came back to Ljubljana, and of course, I always followed what he was doing, and generally knew what he was doing, and I found it very interesting. And then at some point, when he was in Ljubljana, we said, well, okay, you guys have handlers. What would these handlers look like if we actually introduce them into a programming language? So Mattia and I had the idea that the theory that he and Gordon developed, and that was the main result of Mattia's PhD dissertation, we had the idea that this ought to be, there has to be some form of implementing this as a concept in a programming language. So we started working on that. And eventually the end result was the F programming language, where we said, okay, here's a new idea based on the theoretical work of Gordon Plotkin and Mattia Pretner is we can program with algebraic operations and handlers like this. This is F. So it was very much joint work with Mattia, and so I would have never done that if Mattia wasn't around with all his handler stuff.
I see. Can you give a brief explanation to the audience who is not very familiar with effect handlers? What is it about?
There are different entry points into this explanation, but so the first one is maybe to realize that there is something called computational effects, which is things which are not just mathematical calculation of functions. So it is a fact that if you calculate in mathematics, if you compute the same expression twice, you will get the same result. If I calculate the sine of 30 square root logarithm 2, and then I do it again, it's the same number. But in computing, if you run the same piece of code twice, it will not necessarily give you the same result. That's one aspect of knowing that there are effects. There are lots of effects, input, output, state, exceptions, whatnot. People in programming languages have always been interested in them. One important milestone was Eugenia Moggi's account of computational effects in terms of monads, which is heavily present in the way Haskell is designed, for instance. And then, I think already soon after Eugenia Moggi came up with the idea that effects are monads, soon afterwards, John Power was telling people, they're monads, but they're not any monads. They're monads that arise from algebraic theories. So what John was saying as a mathematician was general monads, they describe computational effects, but an even better way to describe computational effects is in terms of algebraic operations. That is to say, you think of things like print and read, an open file, and store something in memory and raise an exception. You think of these things as some sort of primitive operations. And you can explain them that way. And in addition, these operations satisfy equations. So, for example, if I read a memory location and then I read it again immediately, will I get the same result twice? Yes, that's an equation. If I read a memory location and I get X, and then I store X back into the memory, I could just skip storing. It was already there. That's an equation. If I read a memory, if I write to a memory, if I write X into memory location and then I read it, I didn't really have to read it. I know what was there. So these are all equations. And so it turns out that many, many computational effects can be explained in this way. So that you have some operations and they satisfy some laws of algebra. Now, this is very, very good. Anytime you have laws of algebra, this is what allows you to manipulate things, to calculate things. If you think about it, what is it that allows you to calculate integrals? Why do you know that the integral of x cubed is 1 over 4x to the 4? It's not because of the crazy limits that are used in the definition of the integral. It's because after you have defined the integral using crazy limits, you establish some laws of algebra like per partes, and that you can take out constants, and that if you have a sum, it's a sum of integrals. The integral of a sum is a sum of it. These are algebraic laws, and these are really your road to calculation. That's what if you want to calculate, it has to be algebra. There has to be some equations. Lambda calculus is like that. It's algebra. The beta rule that says how you apply a function to an argument by putting the argument into the body of the function. That's an equation. So you have to have algebra. And so this was I believe the way I understand John Power's comments is that he was saying, people, please don't ignore the fact that a lot of these effects are described in terms of algebra. They're operations and they're equations. You should use this fact. And so in the early 2000s, Gordon Plotkin and John Power did this. But there was a stumbling block, which was exception handlers. So when you have exceptions, every programmer knows that you can catch exceptions. Nice. So that was not an algebraic operation. And they didn't know what to do about it. Okay, they said it's something, but they could see it's not an algebra. Catching an exception is not an algebraic operation. It's an effect, obviously, because you catch exceptions, but it's some sort of effectful computation, but it's not an operation. And so then Mattia, in his thesis with Gordon, said, it's a homomorphism of algebras. So some more algebra comes up. And then he said, what are other homomorphisms? And the answer is handlers. So this is the mathematical road. What's the programmer's explanation of handlers? Because that's what you asked me about. It's a generalization of exception handlers. I think that's the best way to understand it. If you look at the proposal for effect handlers in WebAssembly, okay, so there is a proposal to introduce effect handlers into WebAssembly for promotional and propaganda reasons. They didn't call them handlers because they knew they were going to scare away all the other people who want to do WebAssembly. They called them resumable exceptions. And I think that's also a very good name for it. So so an operation is like a resumable exception. It's an exception that happens, but if you want to, you can go back and continue from where it came from. Not only that, you can pass some information back in. Okay. What is a handler? Well, a handler is a handler. So there are exception handlers like the catch blocks, yeah? And the handler is just exactly the same thing as a catch block, but it can catch these resumable exceptions, which another name for them is operations, algebraic operations. And then it can do whatever it wants. And one of the things it can do is it can resume them. It can say, oh, actually, wherever that happened, let's go back there. And let's also pass some information back in. Yes? That's what handlers are. I don't know how operating systems work in the latest and greatest operating systems. But do you know at least how they used to work? How does a program call an operating system call? Like have you ever thought about this? Do you know? You're on Linux, you're a process, you're in user mode. Okay, you're in user mode. You're not the kernel. You can't do whatever you like, and you want to read from a file. You cannot directly access the hardware. You have to go through a system call. How does the system call happen? Yeah. How does the system call happen, actually?
You put things in the stack, and then you give the control to the kernel, right?
How do you give the control to the kernel? You raise a trap, right?
Right.
Right. On the CPU, you execute what is essentially a CPU level exception, because you say, I now do something to get the supervisor mode's attention. The supervisor mode, I need to switch to the supervisor mode one way or another to become the kernel. And the way you do that is you do something bad that lets the CPU say, oh, what are you doing, right? The something bad is called a trap, right? So it's literally already there. The operating system is already doing operations and handlers. It's just what we did in a way is we just said, oh, here's a structured way of doing this inside a functional program.
I was like going back to what we were talking about, the physics is explaining the cathedral, right? Because the effect handler is already there in C, and how OS is already done. And now we go back and we're trying to give a better foundations on what is actually going on there, right? Mathematically speaking.
Well, I mean, in a way, let's be honest, people who design operating systems know very well what's going on there, right? It's more like us functional programmers, we have a certain sense of beauty that we are proud of, right? And would like at a certain sense of how things should be done. Like, for instance, we value things to be done in this structural way, and maybe using types, and we want to be close to category theory and stuff like that. Whereas maybe if you're a Linux kernel hacker, you don't care about those things. But we want to have an explanation of some of these effectful computation phenomena done in this particular way. And this was very successful because monads are an example of that. Monads are this nice mathematically inspired structural way of organizing effects. Well, so are handlers and algebraic operations, but they are a little more special. So every algebraic effect and every algebraic effect induces a monad, but there are monads that are not of this kind. The continuation monad being the prime example of that.
So you gave a fantastic series of lectures at OPLSS, and they're available on YouTube, about algebraic effects and handlers. And I was obsessed with these lectures in grad school. And one of the things you said there was that I think it was non-termination is the most interesting effect. And you never explained it, and it bothered me for years and years.
And you've been waiting for
to explain that now.
Okay, so first there are some general mathematical facts that immediately tell us that non-termination ought to be a computational effect, because if you think about how we model how do we model mathematically non-termination, the answer is with domain theory. So what is in domain theory, when you have a data type, it's a domain, and every domain has a bottom element, which we can call undefined. It's called the bottom. And in Haskell, it actually is drawn like a little bottom symbol, upside down T. Yes. So that element is the one that is the meaning of non-termination. It's like, that's the one, right? Okay. So it's a mathematical fact that you can think of these bottoms, domains with bottoms. There is a monad. It's the monad of adding a bottom to a poset. You already have your domain, and then you add a bottom, or you have a set and you add a bottom, and then if you add two bottoms, you can squish them into a single bottom, and that's bind and so on. So there is a monad. Because there is a monad, it has to be a computational effect. In a way, every computational effect, every monad presumably can be seen as possibly some really strange computational effect. So that's the first point.
Well, does that differ from the maybe monad?
Oh yes, you're walking right into it. So I got you where. Okay, so how does it differ? There's something you can do with the maybe monad that you cannot do with bottom. So let's have an analogy. So the maybe monad has the nothing and the just, right? The maybe monad has the constant called nothing, which is no value, whereas non-termination has a special bottom value, which is the meaning of when the program just runs forever. You say, oh, that's the bottom. Okay, what is it that you can do with the maybe monad that you cannot do with non-termination in a program? You can handle maybe, but you cannot really handle nicely non-termination. That is to say, if you have something in the maybe monad, you can check to see whether it is just X or it is nothing. You can, right? And so if you map out of the maybe monad, how do you map out? So if I have maybe integer and I want to map it to something, I will say, oh, there are two cases I need to do. One is if I have just, then I do this. And if I have nothing, I do that, right? Do you follow? It's going to be two cases. It's going to be a case statement, okay? So in terms of handlers, you just produced a handler. That's what a handler for the maybe for the exception monad is. Can you do that for non-termination? What would that mean for non-termination? So for non-termination, that would mean I have a piece of code and it's calculating, and maybe, perhaps, it's non-terminating. So it could be bottom if it's non-terminating, but if it's terminating, it'll give me an integer. What would it mean to handle it? It would mean you wrap it in some bigger piece of code, and this bigger piece of code is going to say, oh, if it's an integer, then I do this, but if it's bottom, I do that. Can we do that? No. That's the halting oracle. That would be the halting oracle, because it would say, oh, if the program halts, I do one thing, and if it doesn't halt, I do another thing. That's halting oracle. It can tell whether it's going to halt. So that's why it's the most interesting effect, because you cannot handle it. You cannot handle it naively. Once you are in the, it's not, it makes you follow the general rules of how information is processed. You cannot escape non-termination, right?
But that makes it sound like it's like a worse version of maybe, like you've just removed information and then suddenly you get...
yeah, of course it is the worst version of maybe, because I mean, everybody will agree to that. Well, maybe. So it's like the the difference with the, okay, so this is like the difference between the blue screen of death, okay, where Windows told you that it's dead. That's the exception. You can tell that it's dead. But non-termination is when it's just spinning and it's not responding to you, and you have no idea whether it's going to come back or whether it's really spinning, and maybe if you wait longer, it's going to say, okay, now I'm done. What is it that you wanted? That's that's non-termination. So yes. So I don't know. You tell me, which is better? A program that sec faults and tells you I'm dead, or a program that just keeps running and you have no idea whether it's ever going to come back. But that's the difference, right?
I love it.
I don't know. I don't know if I explained non-termination in a way that scratches your itch from many years ago.
Well, was there work on like non-termination is special because that's like it's much more powerful, it seems like. And but is there work that like talks about that shows that
you could say that all of domain theory is like that, is about it.
All of domain theory does it. Okay. Yeah. It's one of those things that like, yeah, there's a very clear connection if you know a lot about domain theory and you know a lot about algebraic effects. And there's no paper to publish about it because there's nothing kind of new there.
Well, nowadays maybe, but okay, so maybe we can say, okay, so maybe I can say one more thing about why I think it's the most interesting effect, okay? So a lot of effects that you have, you can just naively model with usual sets. You just say types are sets, okay? The integers are the set of integers, and the natural numbers, the set of natural numbers, and so on. And the functions are just functions between sets, which are further sets. You can just do everything with sets, okay? Can you really do everything with sets? Well, no, because if you have recursion, okay, then you can define weird non-terminating functions. And so you can define non-terminating computations. So I can define a non-terminating computation of type NAT. Okay. In Haskell, easy exercise. Define a non-terminating computation of type NAT. Okay, fine. Then I ask, well, okay, it's of type NAT. Which natural number is it? It's non-terminating. So then you say, well, it's non-terminating, so it can't be any natural number. Clearly, we have to add another element to natural numbers. Let's call it undef, or let's call it non-term. Yeah? It's a new element. But here is now the catch. 5 minutes ago, we were discussing the fact that there are two kinds of ways of adding an element. One is the maybe monad. The other one is this weird non-terminating thing. It shouldn't be the maybe monad. It should be this non-terminating thing. But this is not a set anymore. It's a partially ordered set. You have to introduce extra structure. You have to say, my numbers are a set, but non-termination is below because it is less informative. If I'm staring at a computation that is never going to terminate, I know less than if I'm staring at a computation that gives me a number. So, and it's just the nature of computation forces you to say, these are not sets anymore. We really should be thinking, we have to put the bottom at the bottom, and functions have to be monotone. They're not allowed to turn things around, because that would mean that they're creating information out of thin air, and that's going to be bad. And that explains that we shouldn't be using sets. That's why it's interesting, because it kicks you out of a naive view. It starts to do real math. I mean, the next step after that is that you say, well, it can't really be just posets. They have to have special properties. And then you're already, at that point, you're already knee deep in domain theory, and it gets deeper.
So you talked about also the continuation monads. So what do you think are algebraic effects getting us closer to like God's effect abstraction, or like the one true one? Or actually, this reveals this is not going to appeal to a relativist. Actually, this was just after the Phil Wadler episode where that would have appealed to him. But yeah, do you think that we're getting closer to something like the right way to do effects?
Okay, so I think it's important to keep in mind that we're in the business of programming languages here. We're discussing programming languages. And first of all, we already have very good accounts of effects, monads being one of them. And then now these algebraic effects and handlers are a very nice account of certain kinds of effects. But because we're in the business of programming languages, we are more generally in the business of computing. But computing is a very open-ended term. Okay, so there are lots of people who are putting lots of money into having new kinds of computing, be it quantum computation, biological computation, and whatnot. And if you look at the history of computation and computers, how they have developed, the humans are developing new ways of computing. It started with maybe abacus, and then it really took off once we had the universal Turing machines or general purpose computers. But even general purpose computers have developed a lot. The first ones that I use had zero parallelism and no distributivity, right? Now computation is very much also about distributed computing. It's also very much about parallel computing. So what am I trying to say? New effects come into existence, effects that we haven't seen before. At some point, somebody said, oh, parallelism, that's a new effect. And then not so many years from now, maybe somebody will say, oh, quantum, actually they already have quantum, that's a new effect, right? Or probabilistic computing, that's also an effect. So a new effect, as we develop our idea of what computation is, and it becomes richer and richer, I would imagine that we will be also new demands will be imposed on any mathematical explanation of what's going on. So I would imagine that it's going to develop in the future. So right now, we can't really tell how we're going to have computational effects that are not accounted for by monads. The monads seem really good at this, right? But who knows, Who knows? I'm not going to predict saying, oh, for the next 1,000 years, every effect that anybody comes up with is going to be a monad. Well, certainly not, because already people came up with co-monads, and those are also kind of effects. So I'm totally relativist there. But in this case, it's really more about the fact that we are in a business that is very much related to the real world and the fact that the real world changes, and that we have, so this is the first thing I tell students when I teach principles of programming languages. I say, we're in the business of setting up interfaces between humans and machines. That is what a programming language is. Never forget that. If we didn't have any humans, machine code is good enough. A machine has no need for Haskell. It already has a CPU. It's happy. It's doing whatever it's doing. But since there are humans who want to tell machines what to do, now we need to do something about it. It's called programming languages. And so if you keep that in mind, you will see that in a way, PL will never be done so long as people invent new kinds of hardware, new kinds of computation. As long as maybe it's just like sometimes it's just something else. Like, for instance, once we went from floppy disks to hard disks, suddenly there were new phenomena that were unknown before.
I think this is the perfect segue for me to ask you about your current research with Bridge and doing something related with AI. Can you tell us more about that? Because the reason why it's the perfect segue is because the world is obviously changing in a really, things are going crazy right now with AI. So what is going on?
People are definitely going crazy about AI. I don't know if things are going crazy with AI. After all, I'm a mathematician, so by nature, more of a conservative animal. Mathematicians are really bad at adopting new things. Really, really bad. They still use notation, totally inappropriate notation, broken notation from I don't know what century, for integrals, and they have no idea how to handle bound variables correctly and all that. They're really conservative. Whereas every functional programmer has a very good idea of these things. So I am somewhat conservative, and I am also conservative about thinking about what AI is doing. And I think I know a little bit I know enough about AI to know that it's not the current one is not the ultimate solution to all problems that humanity has ever faced, even though maybe some businesses are behaving like it is. So let us just leave the bubble alone, let it burst, and so on. But what seems to be clear is that this is a good time to seriously investigate what the role of AI could be and will be in proof assistance, because it's going to take some time before we make it really useful. It's not going to be ready-made. It's not just I drop an LLM on top of a proof assistant and all problems are solved. Far from it. And so it's a good time to do it. And so in the Bridge project, we kind of wanted to use the advantages that we have in our research group, because we have here in Ljubljana, we have people who are really good at producing lots and lots of mathematical data and organizing it. So you know, they have these large libraries of interesting mathematical objects. And it's a lot of data, and it goes into gigabytes easily. And that's a fertile ground for machine learning, first of all. Like, just not knowing anything about machine learning, the one thing you do know is that they love data. So if you have lots of data, they're going to come and look at it, and they'll say, oh, what could we do here? So that's one idea that we have, is that since we do have already all this mathematical data, we can ask, well, what can we do with it? What can we do with it? And the Bridge project is trying to, it sort of has two components. One is make all this data more easily available for machine learners and proof assistants. By the way, it's also useful for proof assistants for certain kinds of tactics, like quick check. Okay, so you know about quick check in Haskell? Yeah. So how does quick check work? Well, it tests your function on a bunch of examples, right? Okay, so now suppose I have a statement about Noetherian rings, whatever they are, okay? And I want to quick check it. It's not so easy to come up with examples of Noetherian rings. But if I have a database of them, then I could use the database and I could have like a quick check on that. So you can do heuristical searches, you can do quick checks, you can try to look for patterns, you can use databases of mathematical structures in machine learning to quickly test hypotheses. I have your machine learning algorithm says, oh, what if this is true? You quickly search the database, you find the counterexamples, and you say, bad machine. You know, reinforcement learning, bad machine. So this is the direction we're going in. So that's the first part, is to actually provide the data. It's more complicated than you would think. So if you might have somebody from the machine learning community and you tell them there are 100,000 theorems in Mathlib, in Lean, and they all refer to each other and they make this huge graph. And then they say, oh, a huge graph. Yes, I want that. How do I get it? And then you say, well, you do some meta programming in Lean. And they're going to say, sorry, I'm not going to learn meta programming. So it's kind of even like at this trivial level, right? It's kind of trivial, but it's not trivial. To have really good data easily available is in itself, I think, a worthwhile effort. So that's one component of what we're doing. Make it available, because we're connecting people. The mathematicians, they have their databases. The databases are stored in zipped files of size 30 gigabytes, right? Okay. I mean, as a computer scientist, you say, like, why do you have a zip file that is 30 gigabytes? How do you think that's useful? Why is it not a database? And then the mathematician says, I have no idea how to make a database. So we're connecting this glue. We're trying to make, like, connect things. That's the first aspect of it. The second aspect is provide bridges. That's why it's called Bridge. Bridges between mathematicians and these formalizers and machine learners, make APIs, provide easily usable gadgets that they can use. That's the first part. The second part is we want to know whether what we're providing is useful, so we should try some machine learning on it. So there is one part of the group is doing machine learning, and for instance, a specific goal is the following. It's called a recommender system. Okay, so if you're in Lean or in ROC, not so much in Agda, but say Lean and ROC have this facility where you can say, here is my current goal. What theorems could I use to derive this goal? Okay. So suppose it's an equation, some equation. Okay, so right now the existing tactics will go through the library of everything that, like all the libraries that you loaded so far, and it will list the theorems that you could use that are applicable. It knows that they're applicable because the goal is unifiable with your current specific goal. But then, it'll say things like every time it will tell you you could try to use symmetry, and instead of proving A equals B, you could try proving B equals A, and you could try using transitivity. So maybe you can come up with an intermediate C such that if A equals C and C equals B, then A equals B. So it's going to give you all these crazy theorems, and maybe if it's natural numbers, it's going to say, oh, you're trying to prove A equals B. Why don't you try to instead prove that the successor of A equals successor of B? So it's going to give you a lot of really dumb advice. Okay? And not only that, it's going to give you a long list, like 50 items of advice, okay? And ordered randomly in the order where that is found, or maybe sometimes ordered by how many premises it has, so that the ones that have fewer premises are at the top because they're likely going to be more useful. Okay, so suppose you want to improve that. That's like Google search. You ask Google, give me all pages that say Haskell, functional programming. And then the reason that Google is so good is because you will only look at the first 4 hits, right? But they always seem to be the useful ones. So the usefulness of Google is not that it knows these pages. It's that it knows how to order them and show you the top. Okay? We want to have that for a proof assistant. We want to have a recommender system for a proof assistant where you say, at this point, I'm trying to prove this statement. What could I use? I want it to give me a list of things where the first 3 hits are interesting. I don't want the first 3 hints to be stupid stuff like A implies A, and like that's I already know that the A implies A. So that's one of the goals of, like, that's one of the stated goals of what we will explore in Bridge.
It reminds me a little bit of the search in ROC. It's pretty good actually because it ranks a little bit. But I have no idea how they're doing that.
As far as I know, it ranks. So suppose you find 2 theorems which could both be used to prove the goal, but one of the theorems has 2 sub-goals and the other one has 5 sub-goals. Which one goes first?
2.
The one with 2 sub-goals.
Yeah.
Because in fact, if you find one with 0 sub-goals, you're done.
Right. So
you just have 1, right? Okay, and then you say, okay, but maybe it's better to have 2 small sub-goals than 1 huge sub-goal. But then you start thinking about what is the meaning of the word small and huge.
Right.
Right? So you can order something, and the ROC is trying to do its best. But, we live in the age of AI, so we can hope that if we show AI every example of every application of a theorem in Mathlib, and there are a lot of them, it might get some idea as to what is going on.
Talking about Mathlib, I think this is a good opportunity for me to ask you, what are your feelings towards Lean having pretty much won the theorem proving war at this point, right? Because giving a little bit of background for the listeners, I did my master's in ROC. I went to the US to learn more about ROC, and in the middle, halfway through, Lean come up and starts like completely dominating the scenario. And I feel like in some sense we kind of like we already have done so much great research into improving and programming languages, and Rock and Agda and Isabel, all of those things already exist and are beautiful. And Lean come in and show that, well, maybe all of this constructivist stuff that we've been so worried about is not so important, really. What is actually important is all these other usability features that is getting in the way, and that's what they did, right? What are your thoughts on Lean?
First of all, I think we're in a typical situation where there are it's software competition. It's like which operating system is going to win, which programming language is going to be more popular. And we all know from experience that what determines the winner is not the quality of the product necessarily. So that's the first thing. But I think in this particular case, I think you have a point there. Maybe the designers of the previous proof assistants maybe they underestimated, or because they were in academia, they could not actually afford to invest a lot of time into usability. Lean definitely wins on usability. The fact that it has this interface where you control click on anything that you see and it takes you to the definition. Whereas if you want to have the same thing in Coq, you have to install you have to calculate the tags file in a make file and run make, and then you have to know what this is in Emacs, and maybe you don't like Emacs, blah 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 blah. So This is not to be underestimated. I think this is a big point. Right? It's a big point. Yes. Then there is the deeper question of constructive versus classical. Yes. Well, mathematicians are classical. Why would they use a constructive proof assistant? That doesn't make any sense to them, right? I mean, like if you do algebra for 5 minutes, you will want the existence of maximal ideals, and then you say, "Oh, in Rock, how do I prove that maximal ideals are around?" And they say, "No, constructive mathematics, you have to reformulate your algebra in this funky way, and then you can pretend that there are maximal ideals," and they're going to say, "Sorry, I'm not going to do that." Right? So it's again, in a way, it's a matter of usability, but now it's at the level of foundations. So you see that for the kind of math they want to do, how they usually do math, what kind of math they want to do, it's just not going to be good to give them a constructive foundation. So let's not forget that the constructive mathematicians are a tiny minority in the world of all mathematicians. So that's it. Overall, I have to say that, of course, Lean has done something extremely important that the previous proof assistants didn't really do. It entered the world of mathematics, right? So Agda and Coq, they were much more, they existed in the world of computer science, theoretical computer science, or formal verification, software verification. They actually arguably they at least partially came out of that tradition. Coq still and has always been also advertised as a tool for software verification, and it is. So as such, it wasn't really able to draw the attention of mathematicians unless they were special kinds of mathematicians. But now, all mathematicians have heard of Lean, right? And they say, "Oh, Kevin Buzzard, Peter Scholze, these are real people. Why are they using this tool? What is going on?" Right? So this is important for the math community. It's sort of made the math community aware of formalized mathematics. So in that sense, it's very, very good. Yeah. I don't know. I don't know that, So maybe you worry that Lean has got the wrong type theory or a badly designed type theory that doesn't satisfy canonicity or whatnot. But apparently this kind of purism isn't that important.
One thing that I learned also when you were talking about the things on how what allows you to use all the how to compute the derivative is all because of the equality, the lemmas that you prove on equality, and you can use them to computer stuff. I just learned this week that that's how you actually do simplification or computation in Lean. Is like you actually are putting all of those equalities into a big database, and then when you call simp, that's what is going on under the hood, and completely blew my mind because it's not what I was expecting. Come from a rock background, right? I was expecting no. These are just gonna do the usual computation rules, beta, eta, whatever reduction, like no whatever equality is under the hood. Like I have to call that explicitly, but again, they have a very different mindset on how to come up with a proof of system there. That's what blows my mind, right? Like they're doing things very differently than Rockhack that Isabel has been doing along the way.
Well, Leo, the main designer of Leo de Moira, the main designer of Lean, he's a really, really good and experienced software designer, right?
I call him the Linus Torvalds of our field,
Yes.
Really good.
So he knows what he's doing. Let us not forget that there is also Isabel, which also works with equality the way that you described.
I didn't know that. Okay.
Yeah. So because it's just a simple type query, you say you install these equalities and then you do rewriting. Maybe here's one point: if you insist that all your equations have to have a computational character, that is to say they are directed, they go from left to right, and then maybe you also insist that they need to be confluent and normalizing and so on, then you do to my mind, you are doing a very particular kind of computation. Okay? It doesn't even have effects. It's a very particular kind of computation. Whereas if you do if you can throw in like arbitrary equations and then you try to use simp, that's algebra. That's really what you do when you manipulate expressions in algebra. So for instance, sometimes in algebra what you say is, let us add 1 and subtract 1 here, because then when we added 1, something nice will happen. So that's not something that Coq will easily do. It's really algebra. It's symbolic manipulation. But the mathematicians do that all the time. They need this. So it's not surprising that they're happy that they have it.
And again, you have to be a little careful how you allow those things. And apparently they have a very, very strong algorithm under the hood, building an ordering graph to make sure that you're not ending up in rewriting things that you shouldn't be rewriting at some point, right? Like make things smaller somehow. But yeah, it's awesome.
It's what you would want, right? Because if you're mechanizing symbolic manipulation, you want it to behave like a human. A human is not going to say, let's add 1 and subtract 1. Oh, plus 1 and minus 1 cancel. Oh, let's add 1 and subtract 1. Oh, they cancel out, right? No human will do that, so the algorithm shouldn't do that either.
Also talking about community, you've also been quite active building community, building ways to foster conversations.
Because I saw that people there needed to be a forum for people to speak in a common place. There was the Rock Zulip, the Lean Zulip, Mastodon, and it was all fragmented. And I thought, well, this is a shame. Let's try what would be a forum that would a meeting point, and Stack Exchange is an obvious meeting point. And that worked really well. I mean, people jumped on the wagon and voted for it, so now we have it.
Yes, we have it, and we're very glad that you pushed that. But it's also sad at the same point that this I feel like with ChatGPT and all that, the community is kind of stopping to be so active in asking those questions and answering questions. Like people are drawing more into asking questions into the LLMs instead of other people, and people are even stopping using Google. So that's something we're gonna see how it's gonna turn out in the future. But yeah, thanks about that. Thanks for that. That is awesome. There is a couple of questions on philosophy and reflections, but I think the most important stuff we had touched. I think let's end with some kind of advice for young researchers and people starting their careers now. What do we What do you wish someone told you when you were starting your research career?
I don't know. I was pretty idealistic and also very lucky that things worked out. I mean, I have nothing to complain about because I was accepted at CMU. It was like perfect environment. I had my advisor is Dana Scott. He was great. So what did I wish somebody told me? I don't know. I don't know if anything comes up right now. I can tell you that I can tell you what I tell my PhD students when they come. I tell them, well, now you're not. PhD is the time where you learn how to leave the nest, right? You have to like, do not try to just do more schoolwork. It's not schoolwork anymore. You are really learning how to be a grown-up. It's at the end of it, you should know things your advisor doesn't know. And the way you're going to do that is that you sort of explore the things that you're interested in, and with a bit of luck, your advisor is going to see the value of that and will be very happy. So I'm the happiest when I have students who are who have some sort of a self-drive, that's where they explore things and they want to do things, and they're not just waiting around for me to tell them what to do. So that's so I think that also, if you're a starting researcher or starting PhD student, don't be afraid to do that. Okay, so do it. Yes. So maybe you're going to reinvent the wheel once or twice, but you will learn a lot, and then there will become a time where you do something original, and you will be very proud of that. So maybe that's like, don't be afraid to do it by yourself. Do it.
How do we learn to grow this inner sense of how to trust in my guts that this idea is worth pursuing?
Who says you should do that? I mean, I have plenty of attempts that didn't lead to anywhere. You just don't know about them. So that's you have to. There's a very strong selection bias there. You only ever see the positive results that people tried. So maybe there's another piece of advice I give to my undergraduate students. I tell them, you should know that the normal state of affairs for a mathematician is that they don't know what to do next. Right? 90% of the time, when I'm trying to solve a problem, I don't know what to do. That's the normal state of affairs. So, where you don't know what to do in a homework or in an exam, you are right where you should be. So that's it's a little bit similar to how do I trust my gut that I'm doing the right thing? Okay, so how do you know you're doing the right thing? Well, that I think is a really a personal question. So some people like to do something because they have an inner drive of aesthetics, and they say, I find this, I want to do this because I want to do it. It's my personal drive that I want to do this. But I think the other people are really more like, oh, I want to do something that will have impact. Maybe an impact on technology. Maybe I want to do something that will have an impact on my community. I want to maybe say, oh, I think if we did this, it would be very useful for future research. So let us do it. So these are all different motivations, and I think a lot of them are valid. One that's maybe a little bit invalid and it doesn't work anyway is I want to do things so that I'll become famous, because that's not going to work. So I think you need to have a sort of, you do have to think about why you are doing the things you're doing, but you also have to be realistic about it, right? And maybe listen to yourself. What is it that you find satisfying? So I certainly am very much a people's person. I feel like I'm a member of a community. I want to work in the community, but not everyone is like that. Some people really want to say, oh, it's me and math and nothing else, right? And that's a different kind of person. And it's luckily we're not all the same. So, you have to figure out who you are. But whatever you're doing, don't be afraid to do it, because that's If you don't try, you're guaranteed not to do anything. You have to try. You have to keep trying. Keep in mind, 90% of the time, you don't know what to do. And that goes also with you don't know where it's going to take you and whether there is anything worthy at the end. That's what real research is, right? If you see a research proposal that spells out exactly what they're going to do, and that's not a research proposal because they already know everything. How is that research?
That is so frightening, though, because we're betting all of our careers into getting to somewhere that we have no idea how we're gonna pan out, if it's gonna work, and especially I don't know, with all the job market being so crowded today. I don't know, like
only that is true. Okay, I'm going to use really hackneyed phrases here, right? Is the purpose of your career to have results or to explore? If it's to explore, I think that is a more viable career than it is to have good results. You should think about exploration. What is important to explore to you, to the community, for applications? Which things would be important to you? So for some reason to explore them. Is not what do I do so that I get good results? No. You will succumb to fashion, fads. You're going to do machine learning, even though you really prefer to do type theory. Don't do that.
I feel called out right now. That was my first option when I was an undergrad and things didn't work out. And I was lucky because now I'm here, right? This is what I wanted to do all along. But oh man, this was great. Thank you so much for your time. Thank you so much.
Thank you so much for having me. It was a pleasure.
Oh man, I hope you guys enjoyed this episode as much as I did recording. Andrej is so incredible, so wholesome, so knowledgeable. This was a great episode. I apologize, a little bit of behind the scene that I'm gonna tell more on the Type Theory Exists for the patrons, as I mentioned, is that I actually kind of messed up with the times. a couple of things with Andrej, and he has been so patient with me, and he's so wholesome. It was so great. And yeah, I'll publicly apologize for messing up. I'm so bad with time zones, but things end up really well. Dan could join us. Thank you so much for your presence, Dan. And yeah, I'm gonna do in this extra episode that I'm gonna record. I'm gonna do a little bit of a retrospective over the last 5 years. For patrons, open up, tell a little bit about the journey behind Type Theory for All, telling you my motivations, what I envision achieving at the beginning, and how do I see this podcast going forward. Anyways, I hope you guys keep joining the show. You know the stuff. Become a patron. Go to the merch store. We have some awesome merch as well. Hopefully next year I'm gonna release some more merch. And if you have questions, make sure to send. You can send questions on YouTube. Okay, I read everything on YouTube. Engagement's not super high, but yeah, subscribe to YouTube. That's gonna assist us, help us. Subscribe to Spotify, Apple Podcasts, give us stars, send it to a friend. Another way to reach out is sending an email at contact@typetheoryforall.com. I'll see you guys next time. Take care. Happy New Year. Happy holidays. See you guys next time.